In this video, we're going to continue solving a simple linear programming equation with a maximization objective function. If you need to review the question along the lines of what are the decision variables, what are the objective function, what are the constraints, how do we plot this graphically, I encourage you to revisit the previous videos. But in this video, we are going to solve for the optimal solution using the corner point method. So in our previous videos, we graphed this problem so that we had a graphical solution that looked similar to the following. So each of these green lines is a various constraint for materials 1, 2, and 3. Now, as we identified in the previous video, we have a feasibility region, that is the region that satisfies all of our constraints, as this yellow shaded region here. Now, the method that we are going to focus on to solve for the maximization objective function or the optimal solution is by using the corner point method. So what that means is we're going to identify the various corners within this feasibility region. So we have 5 corners. So we have a point here at point A, point B, point C, point D, and there is a point here at point 0, 0 that is point E. But because we know that we are dealing with a maximization function, in other words, we are going away from the origin, we can pretty much automatically rule out point E. So when we recall our objective function, so we previously solved for our objective function, again, see previous videos, but our objective function is right here. So our max z is equal to 40x1. So max z is equal to 40x1 plus 30x2. And now we need to solve for what is the profit at each one of these corners. So it's easy to take a few of these points. So at point A, we know that point A intersects with x2 at point 0, 25. And again, if you need a refresher on how we know that, see the previous video where we plotted this graphically. But we know that point A is at 0, 25. So therefore, when we put this into our objective function, we get 40 times 0 plus 30 times 25, which gives us $750. Okay, so that's the profit that we can expect to earn at point A. Let's look at point D. Point D. Point D intersects at point 35, 0. And again, we covered this in a previous video, so please see the previous video. So we get 40 times 35 plus 30 times 0, which gives us 1,400. And then finally, the point that we can plot with somewhat relative ease is point B. Because we know point B occurs at the x2 coordinate of 25, but we don't know exactly what its x1 coordinate is. Of course, we could approximate it and think that it's probably about 18, but we are not going to do that because it won't be exact enough for our solution. So what we're going to look at is we're going to look at which two lines intersect point B. Well, it is material 2 and material 3. Nope, my apologies. It is material 1, this line right here, that make up point B. Now we already know what the value is for x2, right? The value for x2 is 25. So all we have to do is sub x2 is equal to 25 into our equation. So for material x1. So 2/5 x1 plus 1/2 x2 is less than or equal to 20. We're going to sub x2 equal to 25 into the equation. So we get 2/5 x1 plus 1/2 times 25 is equal to 20, which means that we get 2/5 x1 is equal to 20 minus 12.5, right? 1/2 times 25 is 12.5. So that means that we get 2x1 is equal to 5 times 7.5, right? 20 minus 12.5 is 7.5. Multiply that by 5. So then we get x1 is equal to 37.5 divided by 2, which gives us x1 is equal to 18.75. So our guess that point B was at the x1 coordinate of 18 is approximately right, but of course we are dealing with exact numbers here, so 18.75. So 18.75. So therefore, 40 times 18.75 plus 30 times 25 is equal to 40 times 18.75 plus 30 times 25. It gives us 1,500. Now, finally, we have to solve for point C. Now, point C is a little tricky. It's somewhere about less than 20 and somewhere probably a little more than 25, but we don't know exactly. So we're going to look at the two lines that intersect to make point C. So our two lines that intersect are our material 3 and our material 1. So solving for point C, so solving for C, we're going to solve first for our x2 variable. So what we're going to say is that 2/5 of x1 plus 1/2 x2 must be less than or equal to 20, right? This is the constraint that we have for material 1. We'll call this equation 1. Equation 2 is our second constraint line for material 3, which is 3/5 x1. 3/5 x1 plus 3/10 x2, and it must be less than or equal to 21. So I'm going to choose to rearrange equation 1 to solve for x2. So 2/5 x1 plus 1/2 x2. We'll get rid of the inequality, so we'll say is equal to 20. So that means that 1/2 of x2 is equal to 20 minus 2/5 x1. So that means that x2 is equal to 2 times 20 minus 2/5 x1. So x2 is equal to 2 times 20 is equal to 40 minus 2 times 2/5 gives us 4/5 of x1. So from there, we're going to sub x2 into equation 2. So our equation 2 was 3/5 x1 plus 3/10 x2 less than or equal to 21. So then we're going to sub x2 into this equation. So we get 3/5 x1 plus 3/10 times 40 minus 4/5 x1 is equal to 21. So 3/5 x1 plus 3/10 times 40 is 12. And then 3/10 times 4/5 gives us minus 12/50 of x1 equal to 21. So we can rearrange a little bit here. So 3/5 x1 minus 12/50 of x1 is equal to 21 minus 12. Now let's get our fractions in the same common denominator. So we'll pick 50 just because it's easy. So 30/50 x1 minus 12/50 x1 is equal to 21 minus 12, which gives us a value of 9. We can simplify the left-hand side of our equation here. So 30 minus 12 gives us 18/50 of x1 is equal to 9, which means that 18x1 is equal to 9 by 50. So x1 is equal to 450 divided by 18. So x1 gives us a value here of 25. From there, we can solve for our x2 coordinate by subbing back into equation 1. So equation 1 was equation 1 was 2/5 x1 plus 1/2 x2 less than or equal to 20. 1/2 x2 less than or equal to 20. So we'll sub in x1 is equal to 25. So 2/5 times 25 plus 1/2 x2 is equal to 20. Well, 2 divided by 5, 2/5 times 25 is equal to 10. So 1/2 x2 is equal to 20 minus 10. So then x2 is equal to 2 times 10. So x2 is equal to 20. So now we have our x1 and x2 coordinates of point C. So we had x1 is equal to 25, x2 is equal to 20. So we had point C at 25 and 20. Therefore, 40 times 25 plus 30 times 20. So 40 times 25 plus 30 times 20 gives us a value of 1600. Now, because this is a maximization problem, we're looking for the solution that gives us the max profit. In this case, it is point C, 2520. So 25 tons of fuel additive and 20 tons of fuel solvent. Now, I'll just highlight that you'll notice in my drawing that point C isn't exactly on our lines, and this is why we need to find algebraically our coordinates for point C, where our two lines intersect. So the approximation method gives us a good general vicinity, and you'll notice that the point C does look close to 20 and 25 on the x2 and x1 coordinates, but when we solve algebraically, we notice that it's actually much more exact. So point C, that is this point right here, is our optimal solution. And that's it for this video. Thanks for watching. If this video helped make business analytics easy, consider giving the video a like. And if you need additional help with business analytics, please consider subscribing to the channel. I look forward to solving many more problems with you next time.